Apologia, 8th grade physical science, week 11, day 2, textbook pages 170 to 176, notebook page 132 to 136. As you think back over the last section, I hope you realize that we talked a whole bunch about energy. Some of the reactions, such as the decomposition of water, required energy to start them. Other reactions, such as the single replacement reaction shown with the butane lighter, gave off energy in the form of heat and light. The fact is, all chemical reactions involve energy. It's easy to think about combustion reactions giving off energy. In fact, that is often the reason that we want to use a combustion reaction. If you've ever grilled your food on a gas or a charcoal grill, you started a combustion reaction specifically for the heat it produced to cook your food. Just as we classified chemical reactions by the type of reactants and products, guess what? Chemical reactions can also be recognized by the energy changes that occur. So, how is energy used in chemical reactions? The answer is in breaking and forming ionic or covalent bonds. Energy is used to break bonds, and energy is released when new bonds form. If you look at the chemical equation for the combustion reaction of propane, here we go, the fuel we used in gas grills, you can write heat as one of the products on the right side of the equation. So we can just put heat over here. Since the products are formed when the bonds of the reactants are broken, the equation tells us that the heat came from the reactants. Where was the heat energy when it was part of the reactants? Well, remember, we talked about it being transformed from the types of chemical bonds. Well, before the energy was transformed into heat energy, it was chemical energy stored in the chemical bonds of the propane and the oxygen gas molecules. So this heat came from the way these guys were bonded together, the types of bonds that was stored in there. All right, so the definition of chemical energy is the energy stored in chemical bonds. Take a look at what we're looking at here. It is the chemical equation for the combustion reaction of propane, the same one we were just talking about, the fuel used in gas grills. We have all different kinds of single bonds. We have all different kinds of double bonds in the reactants. And then in the products, we have some double bonds and some more single bonds, and then we also have heat. There are 10 single covalent bonds in a propane molecule. 8 carbon-hydrogen bonds, 1, 2, 3, 4, 5, 6, 7, 8, and 2 carbon-carbon bonds. Each molecule of oxygen has one oxygen double bond. Each molecule shares a double bond. And there are 5 oxygen molecules. The chemical energy of the propane and oxygen molecules are stored in these bonds. The chemical bonds of the products also store chemical energy. It is the changes that occur in the chemical bonds that causes the energy changes in the reactions. In the combustion reaction, the bonds of propane and oxygen molecules are broken, while the bonds in carbon dioxide and water are formed. So these bonds are broken, forming these bonds. The extra energy then is over here as heat. Breaking bonds requires energy. Think about your grill again for a minute. In order to start the combustion reaction, you had to provide a spark. If your grill is a propane grill, they have built-in igniters that provide a spark. The spark provides enough energy to start the reaction by breaking the bonds of the reactants. All reactions require some amount of energy to get going. The energy required to start a reaction is called activation energy. This is one of the questions from notebook page 133. What is activation energy? Activation energy is the energy required to start a reaction. All reactions require some amount of energy to get going. Look again at this figure. For each molecule of propane that reacts, 3 molecules of carbon dioxide and 4 molecules of water are produced. Look at the bonds formed in the reaction. We have 6 carbon-oxygen bonds and 8, 8 oxygen-hydrogen bonds, single bonds. When the chemical bonds form, energy is released. So the heat and light you see when you start up your grill come from the formation of new chemical bonds. Once all the bonds in the propane and oxygen models are broken, the carbon, hydrogen, and oxygen atoms rearrange to form molecules of carbon dioxide and water. Another question on notebook page 133. In the reaction below, heat is a product. Where did the heat energy come from? Well, as we just learned, the heat and light that you see when you start up your grill come from the formation of new chemical bonds. Counting with moles. Here we go. 1, 2, 3. All right. Before we can talk about how much chemical energy is held in the bonds between atoms, we need to discuss how chemists count things. You see, atoms and molecules are so small that to talk about the energy of just one single atom is not at all practical. Also, chemical reactions often involve large numbers of atoms, ions, or molecules, so having a way to talk about them just makes sense. You can think about it as just another way to count things. For example, people usually count eggs by the dozen and gloves in pairs. But how would you count grains of salt from your salt shaker? Well, that's kind of how it is when you count atoms or molecules. To give a frame of reference, a single drop of water contains about 10 to the 22nd molecules of water. And each molecule has 3 atoms. It's impossible to count that many molecules, yet chemists need a way to talk about the large numbers of molecules or atoms. Well, in 1811, an Italian chemist named Amedeo Avogadro provided the number chemists could use to describe large amounts of very small particles. Chemists use moles to count atoms, ions, or molecules. So the definition of a mole is an amount of a substance that contains approximately 6.02 times 10 to the 23rd particles of the substance. These are not the moles that live in the forest or one you get on your skin. In chemistry, a mole is a unit of amount. The mole is the SI unit for the amount of a substance. In chemistry, 1 mole of a substance contains nearly this number, 6.02214076 times 10 to the 23 atoms, ions, or molecules of that substance. Since that is such a long number, we sort of round it to 6.02 times 10 to the 23rd. For example, 1 mole of water contains 6.02 times 10 to the 23rd molecules of water. 1 mole of silver contains 6.02 times 10 to the 23rd atoms of silver. The important thing to remember here is that a mole is always the same number of particles. So just as a dozen is always 12 and a pair is always 2, a mole is always 6.02 times 10 to the 23 particles. This is helpful so that we don't have to write out such long numbers. For example, I can say 1 mole of water instead of saying 6.02 times 10 to the 23rd molecules of water are reacting or produced. And since reactions usually never involve just one single atom or molecule, we can compare the number of moles of reactants and products in balanced chemical equations. For example, this. we would be reading that as 1 molecule of propane reacting with 5 molecules of oxygen, yielding 3 molecules of carbon dioxide and 4 molecules of water. But we can also read it as 1 mole of propane reacts with 5 moles of oxygen to give 3 moles of carbon dioxide and 4 moles of water. Notice how I use the coefficients to tell me how many moles or molecules of each substance is used or made in the reaction. All right, back to our notebook, page 133. What does the text say is the important thing to remember about a mole? The important thing to remember here is that a mole is always the same number of particles. That should be here. And 1 mole of a substance contains the same number of particles. The weight and the volume can and really will be different. Bond energy. Now let's talk a bit about how energy is measured. Energy is measured in units called joules, J, named after James Joule, a 19th century English physicist. Larger amounts of energy can be described using the unit kilojoule or kJ for kilojoules. You will learn more about joules and energy in a later physics module. For now, it's important to remember that energy is measured in joules. Each kind of chemical bond has a specific amount of energy associated with it. Bonds with a high bond energy require more energy to break them apart than bonds with a low bond energy. For example, more energy is required to break an OH bond than to break a CH bond. The bond energy is a measure of how strong the bond is. So here we have table 5.5 of some common bond energies. Look at this table. Notice how the energy is measured in kilojoules per mole. So these are just a hydrogen-hydrogen bond, a hydrogen-carbon, hydrogen-nitrogen bond, and so on. How does the energy needed to break a hydrogen-nitrogen bond compare with the energy needed to break a hydrogen-oxygen bond? So let's look at hydrogen-nitrogen, 390, as compared with a hydrogen-oxygen, 460. A hydrogen-carbon bond, 410. During chemical reactions, energy is either released or absorbed depending on the bonds that are broken and formed. Exothermic reactions. Many chemical reactions release energy. Some reactions give off a little energy, while others release a lot of energy. Fireworks, or the combustion reaction of a wood fire, release a lot of energy quickly. A compost heap, on the other hand, releases a little energy slowly as the grass clippings, vegetable scraps, and soil warm when decomposition reactions take place over time. A chemical reaction that releases energy to its surroundings is called an exothermic reaction. So the specific definition of an exothermic reaction is a chemical reaction that releases energy into its surroundings. The combustion reaction of propane, showed in this figure, the one we've been talking about. Here we go. Is an exothermic reaction. When 1 mole of propane reacts with 5 moles of oxygen, about 2100 kilojoules of heat is released. So we can actually just substitute it. Now that we know 2100 kilojoules are released, we can just write that into the equation. Look at figure 5.22. It is a graph showing how chemical energy changes during an exothermic reaction. Notice the chemical energy of the reactants up here. We have the reactants up here. And the chemical energy of the products. Here we go. This is just for an exothermic reaction, the products down here. The reactants have more or greater chemical energy than the products in an exothermic reaction. The difference in their chemical energies is equal to the amount of heat released during the reaction. So this The difference between is the energy released by the reaction. Notice this hump above the dotted line showing the reactant's chemical energy. That hump represents the activation energy, or the energy required to break the chemical bonds of the reactants. To understand this better, think about what has to happen at the atomic level in order for one atom to change places in a compound with another atom. The molecules must run into each other or collide, and they must collide with enough energy to break the bond, or the reaction will not happen. Consider the propane combustion reaction as an example of what I mean. Thankfully, propane can sit in the presence of oxygen at room temperature. We all have propane tanks sitting outside on our grills, or even outside on a hot day, and no reaction will occur. The heat energy of the surrounding air is not enough to result in combustion. But if you add a spark, you increase the heat energy sufficiently so that some of the molecules around the spark move faster. As they move faster, the molecules begin to collide with enough energy to start the reaction. Once the reaction is started, it will continue until one of the reactants is gone, or until the reaction is extinguished by outside means. So back to our notebook on page 135. Using the graph shown, explain which has more energy, reactants or products, and how you know. Again, for an exothermic reaction, the reactants have more chemical energy. They're higher up on the graph than the products in exothermic reactions. The difference in their chemical energies is equal to the amount of heat released during the reaction. So again, heat will be released during the reaction. So that was exothermic. Now let's talk about endothermic. In some chemical reactions, energy must be continually added or the reaction will stop. This was the case in experiment 5.1. You guys have not seen this yet. As long as the battery was supplying the electricity, the decomposition of water into hydrogen and oxygen will continue. You'll see this in class. Or until all the water was decomposed, whichever occurred first. Another example is cooking vegetables. As long as the vegetables are in hot water or steam, they will continue to cook. But as soon as you remove the vegetables from the heat and place them under cold running water, they will stop cooking immediately. Any chemical reaction that absorbs energy is called an endothermic reaction. So the specific definition for an endothermic reaction is a chemical reaction that absorbs energy from its surroundings. In endothermic reactions, the energy needed to break the bonds of the reactants is greater than the energy released when the bonds of the products are formed. This should say bonds. I must have been in a big hurry to get this done. All right, so look at figure 5.24. This figure shows the energy graph for an endothermic reaction. All right, so notice the difference. In the endothermic reaction, the reactants have a lower chemical energy than the products. Again, so we have the reactants down here and the products are up here. So notice that in these reactions, the chemical energy of the products is greater than the chemical energy of the reactants. The difference between the two, same thing. So again, this difference is equal to the amount of energy that must be absorbed from the surroundings. In water electrolysis, energy must be added to keep the reaction going. So when we write the chemical equation for the decomposition of water, the energy term appears on the side of the reactants. Here we go. So this is the energy. It's on the side of the reactants, not the products. According to this chemical equation, 572 kilojoules of energy must be added to separate 2 moles of water into 2 moles of hydrogen and 1 mole of oxygen. All right, lastly, one important thing to keep in mind when looking at the energy in reactions is that the total amount of energy before and after a reaction is always the same. In exothermic reactions, the chemical energy stored in the bonds of the reactants is converted into the chemical energy in the bonds of the products, plus heat energy, sometimes also light and sound energy. Think of it like this. So in an exothermic reaction, the reactants equals the products plus the energy. It is opposite in an endothermic reaction. The reactants plus the energy gives us the products. So in endothermic reactions, heat energy plus the chemical energy stored in the bonds of the reactants is converted into the chemical energy stored in the bonds of the products. All right. Either type of reaction, though, will have the total energy of one side equal to the total energy of the other side. This is because, like matter, energy cannot be created or destroyed. It can only be transformed from one type into another, and this principle is known as the law of conservation of energy. We'll read more about how energy is conserved in later physics modules. All right, experiment 5.2 we are going to do in class.